Okay, we want to talk about the types of magnetism in this video. We're talking about diamagnetism, paramagnetism, and ferromagnetism. And we want to talk about the types of magnetism in this video. Sorry about that. And then we're also going to discuss which of these types of magnetism is present in Earth's magnetic field. All right, enough on that. So let's start off. This is the weakest form of magnetism, diamagnetism. It's present in all matter. And I suppose I should mention before we get too far along, in your workbook, I'm looking at page 219 in my book. Might be slightly ahead or behind that in your book. And maybe I'll go ahead and get us on one board here. All right. So, and just again, I'm kind of reiterating what's on this page here, but diamagnetism is the weakest form of magnetism. It's present in all matter. However, if either of these other two forms are present, turns out this one is so weak, it's negligible. All right. So, all right. What else did I want to say about this? Oh, another interesting fact. Usually when you see, well, it's very difficult to show this. I've got an example in just a second, but we'll see diamagnetic materials are repelled. And then I want to make sure I make this point clear here. You may want to underline this by non-uniform be external. So what I mean by this is if you bring a magnet near something, generally speaking, the magnetic field near a magnet is non-uniform. It spreads out, it warps. We've seen this over the. So if you bring a magnet near a diamagnetic material, you will actually see it pushed away. All right. And if you think about that, you probably have not seen this in the real world before. You may have seen a magnet repel another magnet, but I don't know if you, right, you may, like if you take a North Pole and a South like this. Where'd it go? Whoops. Here's two magnets right here, right? And I don't know if you can see this, but if I separate them, right, there's two magnets there, right? And what I can do is I can flip the poles and you can see there's some, we see there's a small gap between these two, nothing crazy here, but this magnet is repelling that upper magnet. These are ferromagnets though, right? They're both already magnets. What you probably haven't seen is this scenario over here. Okay, so nothing up my sleeve here. These are two cherry tomatoes, right? You don't usually think of tomatoes as being magnetic. However, they are, and so is all matter. And so I'm going to try and prove that to you using this ginormous magnet here, all right? Technical term. So magnetic field strength is actually, for a magnet like this, the longer the magnet is, the stronger it is. The larger the surface area, the more uniform the field. So we see this should be a very strong magnet, but it should be very non-uniform. We're going to expect magnetic field lines warping all over the place out of here, right? So now I'm going to bring this close, and notice I've got a red pole and a yellow pole, and maybe what I'll do is I'll even mark, I don't know which one's north and south, but it doesn't matter here, just in case you have trouble seeing the colors. I'll have one of them that has a dot on it, and one of them that doesn't. All right, so what I'm going to do is I'm going to bring this pole, and let's just choose arbitrarily to call this the North Pole. So the red is the North Pole. I'm going to bring this close, and hopefully you could see the tomato is being repelled by this. Now you might be saying, well, maybe that's just string, or maybe I'm pushing it with air or something. Watch this. I could stop it, and then I can start it again, rotating the same way. And I think, now keep in mind here, this is a very subtle amount of force, right? We're barely able to twist this string and stop it. So I'm able to twist this thing around here. And watch this. I'm going to switch the pole. And we see it's not like these tomatoes have a magnet hidden inside of them, right? I'm able to repel these tomatoes with either pole and stop it. Let's do it one more time. So I'm just trying to show you that you really can repel a tomato with a large magnet. The issue is you have to have, you really need negligible friction here for this to work. And I'll stop it one last time and we'll call that good. Oh, whoops, that's going the same way. Sorry about that. Right, the whole point of this is to show you that these tomatoes are actually being repelled by this giant magnet. And it doesn't matter whether I use the North Pole or the South Pole. And here's another thing. When I take this magnet away, it's not like you suddenly expect these tomatoes to be magnetized and remain permanent magnets. So that's the last piece of information I want to emphasize about this. If we go back to our board here. It's this one. The magnetism will disappear when B external is removed. So we only notice the magnetic effects of diamagnetic materials when an external field is present. So these last two are the ones I was just showing you with the grapes, right? We see that you can repel these, tomatoes in this case, you can repel these tomatoes with a large magnetic field, but we see that when you remove the external magnet, that magnetism disappears. And to be clear, this is a very weak form of magnet. We can only, weak form of magnetism, we only saw this work when it's delicately balanced by a string and, right, only the slightest of force appears and it's just barely able to twist this thing, which is hanging on a string. So it's extremely, extremely weak, but it is present everywhere. Now, if you use a large enough magnetic field, you could levitate me, although that would require enormous fields. They've done things like levitate frogs and things like this. And so if you're curious, maybe what I'll do is I'll share a screen real quick. If you want to do a web search on your own, let's do this one. So here's an example of them levitating some flowers, and you can see they took some frogs and levitated them and things like this. You could ask whether this is ethical or not, and there's a grasshopper, all kinds of different stuff. So if you want to web search that, that's fine. You can look at that on your own time. All right. So next up, let's get over, and let me make sure I didn't forget anything. I'm pretty tired today. I don't know if you noticed. Okay. Well, let's go over to paramagnetism. And so it's weak. Oops, let's go to blue. But it is stronger than diamagnetism. All right. And this is not present in all matter. And the interesting thing about paramagnetic materials, it's a very weak attraction. And we should be clear, they're attracted by a non-uniform B external. Okay, so basically, when I say a non-uniform B external, I'm talking about the magnetic field near a standard bar magnet. All right. In this case, maybe I'll show you something here. Oops, where did it go? Oh, I don't have it here. All right, well, I lost my simulation, but if you want to do a quick web search, there's a classic image for this where they have a horseshoe magnet like this. So you take an extremely strong horseshoe magnet. Again, this is weak, right? If it's weak, we're going to need strong magnets to make this effect known. And you could pour liquid oxygen, right? So liquid oxygen, you could pour that in there. And what will happen is you'll see the liquid oxygen, instead of just falling straight through, will pile up on the magnetic pole faces like this. And so paramagnetism is actually strong enough to support the liquid oxygen in between the pole faces. And since it doesn't fall down, it's clearly attracted to the magnet. All right. Is there anything else I wanted to say about this? Increasing the temperature will reduce the paramagnetism. So, all right. So that's interesting fact. That's about all I need to say about this. And then let's go into ferromagnetism. That's the type of magnetism most of us are familiar with. So ferromagnetism is the strong type of magnetism, right? There's a number of materials that we usually think of, and let me just write a couple of these. The neodymium, I got to look that up. It's neodymium, iron, and what is that? Boron. So these are the neodymium magnets or rare earth magnets that you'll sometimes hear about. So that's neodymium magnets. Obviously, there's iron, nickel, cobalt, things like that. Alnico, another type. Maybe you'll hear about that. And there was one other I had written here. Magnetite, so naturally occurring. All right, so there's a bunch of different types. Now, ferromagnetism is a little bit trickier than both of these. Oh, and yeah, that brings up another fact I forgot to say about this. These two types of magnetism, para and diamagnetism, both are only present in presence of B external. So to be clear, paramagnetic materials and diamagnetic materials, these two materials, types of materials, will only exhibit their magnetism when you have an external field. So in order to show off diamagnetism or paramagnetism, you need to bring a magnet into the game. Paramagnetism is not like that. It can persist after B external is removed. And I'll show you an example of that. And the other thing is, it can attract non-magnetized materials excuse me, just a second. It will attract or repel other ferromagnets. Oops. All right, so this is a lot of stuff. Again, you've got it all written down there. So the idea, again, let's start with this one. Here are two ferromagnets, and maybe what we'll do is we'll put it up here just so you can see this a little bit better. Let's go over to our demo station here. All right. We're done with our grapes. I'm going to get this out of here really quick. All right. Sure hope I hit the live stream button. Did I? I think I did. Yes, we're going. Oh my gosh. Sorry. I'm really tired today. Okay, so we've got these two ferromagnets, and notice they're attracted together. Right? I could leave them right here. We could see it draws it across the table and it's attracted. An interesting thing, if you turn it the wrong way, we see it repels it a little bit. Now, in order to make this not tip over every time, what we could do, again, is flip this, flip the pole faces. And we see it's levitated above this here, right? So there's clearly a repulsion. When I push them together, it tries to spring apart. So these two are repelled by each other. Now, an interesting thing here, to try and show off some of these other properties, I've got some paper clips. And what I'm going to do is I've got some nails here. And you see me slamming these on the desk a few times in a row. I'm going to get these other magnets out of here. The idea is, if there was any residual magnetism in these nails, dropping it on the table a few times allows the magnetic domains inside of here enough energy to misalign. Now you may say, what's a magnetic domain? Imagine you had a bunch of, hopefully you can see this on the screen. Let's see if I can zoom in even more. I guess that's maximum zoom level. And I'm going to try and use these paper clips, and I apologize if this doesn't show up that well. But yeah, you can see there's paper clips, and some of them are oriented in different ways, different directions. Maybe we should just draw this on the board. Sorry about that. I'm in a new setup today, and so I'm not used to it. All right, so say you have a slab of, oh my gosh, two. There we go. Let's say you have a slab of ferromagnetic material. Inside of here are a bunch of what are called domains, basically regions. All right. And so trying to break this up. Now, obviously we don't see lines like this all over the material, right? But the idea is inside of this material, there's a bunch of electrons orbiting around, right? And in there, you could think of these orbiting electrons as being like current loops. And these current loops all have magnetic moments, right? Well, you could think of that as being like the magnetism of these materials. And so in this case, in this region, this domain, most of the orbiting electrons tend to line up so that they're all pointed the same way. Maybe over here, they're pointed a different direction. And so we get these regions where in different regions of the material, the magnetism on average is pointing in different directions. We say these domains are random, right? Now, what can happen here, in this case, on average, the magnetism is going to kind of cancel out because all these domains are randomized. Now, what I could do is, again, if I'm dropping these nails over and over again, if there was, by chance, some slight organization in here, the act of dropping them on the table provides enough energy to re-randomize them. All right, so we've got these randomized nails. What's an interesting property is, let's say we bring a magnet close. All right. So let's say we bring a magnet like this. Perhaps you recall the magnetic field goes out of north and into south. What do we know about magnetic moments? They have a tendency to align with the external magnetic field. When they do that, we might expect some of these domains to change, like this one, right? Well, when it does that, I don't know if you notice, these two are about the same. This essentially becomes one giant domain, and maybe this one does the same, and this one does the same, right? So these domains get larger and tend to be more aligned, right? So we have this huge mega domain, and maybe this one doesn't perfectly align, but maybe it partially aligns. Maybe this one gets slightly closer to alignment, etc. And so maybe some of these other domains get closer to alignment. Maybe this one goes down to here, etc. And so on average, we're seeing this effect of the magnetic domains starting to align. Great. That means bringing a magnet close to this ferromagnetic material should cause it to be attracted. Now, this is another ferromagnet, right? And it's just going to snap together. So basically, we can take one permanent magnet and cause it to cause these domains to align. Here's the special part. When I remove this external magnetic field, when I take away the permanent magnet, the idea is these domains might relax a little bit, right? So maybe we'll go back to having some domains, but they're going to remain at least partially. Oh, that one was still wrong. Okay, sometimes maybe they don't go completely back to their initial position or to their initial alignment. We're still going to get some partial alignment here. All right, so maybe these go this way and these go partially this way. But what's happening is some magnetism, some ferromagnetism will be remaining after the magnet is removed. This is dramatically different than what we saw just a minute ago, right? We were talking over here. In this case, right? Both diamagnetism and paramagnetism, when you remove the external field, the magnetic effects go away. However, with the ferromagnetism, we see that this magnetic effect can persist. And let's see if I can show you that. All right. All right. So now this is just a glass beaker. And these nails are not magnetic right now. Here's another one here too, actually. Drop it. So I'm just trying to get rid of the magnetism in here by misaligning all the domains. Let's make sure this is not magnetic. Oh, it still is. Okay. It's not a very strong magnet right now. There's still a little bit. I was hoping this would, right? All right. Still slightly magnetic, but not that strong. Some of these paper clips might be partially magnetized, might be the issue here. All right, so this is not acting as a good magnet right now. All right. So now what we could do, we could take one of these nails. This is the old school trick. Whoa, this is a super strong magnet. I better be careful. So what I'm doing right now is I'm running this magnet along the length of the nail, right? And when I do that, that's going to tend to align those domains that we were just looking at, right? As I run this along the length of this material, we expect these domains should align, right? Now, this is a very strong magnet. If I do this a few times, hopefully we can get enough of an effect where we can see this starting to magnetize this nail, and we're just barely able to pick this up. And notice the external magnet has been removed. What we did is we used this giant magnet to align the domains in here. Now again, we could take this, try and get rid of that magnetism, and now it's no longer working. So that's the effect I was trying to show you. The other way I was trying to describe this, perhaps more practical, make sure this is good. So I've got and what I'm going to do now really quick is actually put these paper clips in here, just in case they got magnetized, and shake them really hard. Try and get rid of any residual magnetism that's left in those, right? So hopefully those are all demagnetized now. And the idea here is I've got a coil of wire. All right, now let me make sure this shows up by looking at the screen really quick. Okay, you can see it. All right, in this case, notice the switch is not closed. We don't see much magnetism here. Now, in this case, what I'm going to do is close the circuit and energize this. All we have is a copper wire here. We're probably going to see a lot of amps. All right. So what do you got? 1 point. Let's see. What do we got? Let's crank this up. We've got. All right. That's a small. Oh, we're hitting overload. I see. All right. So we're maxing out the current. But in any event, while this electricity is present, I hope you agree this is a tremendous amount of magnetism, right? So this is a trick. You use an electromagnet. While this coil is energized, the magnetic field from the solenoid that's wrapped around the nail tends to cause the domains to align. Now, when I open the switch here, we see some of the magnetism remains, but it's not quite as strong. So this concept can be used, right? You can turn a magnet on and off, and then you can pick up objects, and if they're beyond a certain mass, it'll drop them. So maybe you've seen those pictures of a device that picks up a car with an electromagnet, brings it over, and then drops it, things like that. All right, there is still some magnetism here, though. All right, so again, all that was just to show this fact right here. We saw that non-magnetized materials like those paper clips could be attracted. And then afterwards, after the external field is removed, we saw that that magnetic field can persist. So this is tremendously useful. We see that an electromagnet is a standard way to do that. An interesting fact, it turns out, let's go back to this demonstration really quick. Like this one. Now in this case, right, I could go into here and I could switch the leads, right? I could switch what's plus and minus, all right? Now in this case, there's still some magnetism here. And when I switch it, now what's happening is the electromagnet is so strong, it can actually flip all the domains completely backwards and still pick up all these paper clips. There is an interesting effect here though, all right? And what happens here is, and this is getting pretty hot here. I'm gonna let go of that. All right, the idea, it's definitely getting warm. Each time you change the external field, this nail will change, but it's not like it changes the same way every time. There's what's called a hysteresis loop. So if you're going to end up looking at magnetic materials more often, what happens is it sort of remembers its history. And so if you first magnetize it one direction, then try to flip the direction, it may not magnetize as strongly the other direction as you would like. And then every time you magnetize it and demagnetize it, you get this strange swooping field and these weird shapes. I'll let you read about that in the book, but it suffices to say the order in which you magnetize a ferromagnetic object will affect the strength of the field in it. By that, I mean, whether you go this way, then this way, then this way, that would be very different than going that way, then this way, then that way, then this way. All right. So basically, the magnetic field strength depends on how many times this thing's been magnetized and in what direction. And there's a thing called hysteresis, and you could read about that if you want. All right. So now that we've gone through all that, hopefully that'll turn off here in a second. Let's go to a screen share really quick. And so in this case, now I want to look at the field associated with these bar magnets. Now, and maybe what I'll do so you can see me is I'll go out to preset 3 here, just so you can see me babbling in the corner if that's still on the screen. All right. Now in this case, just moving this around, you can maybe see some magnetic field lines there, right? Now, I'll just kind of remind you here, whoops, we've been using blue, I think, for this field. Remember, we're talking about field lines going out of north and into south. And you can kind of see that pattern being modeled here. All right, out of north and into south. So the blue lines that I'm drawing represent B external. All right, that's B external. Now in this case, you could think of a compass needle, this jobber over here, as being a separate ferromagnet, and notice it tends to align with the external magnetic field. And I do want to point out, right, this is the North Pole and this is the South Pole. So notice the magnet of the compass aligns the same direction with the magnet of the bar magnet, right? And so notice the North Pole of the compass is pointing at the South Pole of the other magnet, right? A North Pole would stick to a South Pole, just like a positive charge would be attracted to a negative charge in electricity. All right, so if we proceed, we could actually, if you wanted to see inside the magnet, that's kind of interesting too. Look at what happens inside the magnet. This is a little bit different. Notice that inside the magnet itself, the North poles are pointing the opposite way, right? From south to north inside the magnet. And this actually, if I could, you could imagine if I had a current loop here, right? So let's say we had a loop carrying current. I don't think you'd have any trouble thinking, oh, the magnetic field's going to go out and then back in the other side. And we don't expect it to suddenly change while you're on the inside. And that's what's happening here. It goes out, around, and then straight through the middle. And so we see the magnetic field inside the magnet points from south to north, but it's basically trying to give it, I don't know. I like to think of a bar magnet as being very equivalent to a circular loop of wire carrying current, right? In these cases, you could guess. And all right, in this case, just as a refresher, you might think, oh, which way is current flowing in this loop down here, right? So we clearly see the B field is going this way. So what you want to do is you want to wrap the fingers of your right hand in the direction of the loop. And so I view it as, oops, come on, get out of there. Let's get our orange back, right? Current seems to be flowing down on the front side and up on the back side. That's how this loop would produce that magnetic field. All right. So, and yes, it would have a magnetic moment pointing this way, right? So that's the magnetic moment. And we see that the magnetic moment at the center of the loop tends to point the same direction as the B field at the center of the loop. All right. Enough on that. So going on, let's take a look at the Earth. All right. So here is, the Earth obviously does not have a large magnet inside of it, a large bar magnet, but there is a large amount of magnetism inside the Earth. So if we think about this, let's imagine which way the magnetic fields would point. Out of north, around the planet, and into south, right? Out of north, around the planet, and into south. And notice there'd actually be, we might expect a line going straight out this way and maybe a line going straight out this way. All right. Notice the field is going to be strongest near the North and South Pole. And I'm about to put a compass on, well, actually, all right. So there's the external field. Now let's show the field, right? So we've got this field from the Earth that's pointed in the direction we just saw. Now I want you to think, when I add a compass, the North Pole of the compass will point which way? When we add that compass, it tends to point and align with the external fields. So if I could, we'll draw this field again, right? It's going out of north. Right here, we see that compass tends to align, and then into south. Out of north and into south. Now, notice the North Pole of a compass points towards the North Pole of the planet because the North Pole of the planet is a magnetic South Pole. I'm going to say that again. The magnetic field of the Earth has its magnetic south at the geographic north. Okay. And so that's why North Poles of magnets point towards the North Pole of the planet. The North Pole of the planet is a South Pole of a magnet. All right. Now watch what happens here as I move this compass around. We see it starting to trace this pattern. And notice which way the compass points near the North Pole. There is a component that points towards the geographic north, but there's also a component that points perpendicular to the Earth's surface, right? Over here, we see the compass points parallel to the Earth's surface. But as you get towards the poles in either direction, right? And right here is the extreme case. At the North Pole and the South Pole, whoops, the compass isn't going to work very well, right? Because it's going to tend to point towards the ground. Now, obviously, if you hold the compass in your hand parallel to the plane, it would give extremely unreliable measurements, right? Because you could be just slightly off and it would start going haywire. So the idea is, as you get closer and closer to the poles, the magnetic field of the Earth dips towards its surface more. So, all right, that's enough on that, I think. Now, if you're curious, let's see, I think it's, oops, let's go into here. Oops, still on that. I believe the term that you might be interested in. There's a theory about the magnetism from the Earth's core. And if we look at this, we could maybe look at this picture here. The idea is the Earth is not a giant bar magnet inside, right? There's some mechanism that creates this magnetism. And if you want to read more about this, this is one theory that is supported. And this is where they think the Earth's magnetic field comes from. Basically, you have fluids flowing and that acts like current loops. And so you get some magnetism out of that. I'll let you read about that on your own time. It is pretty interesting. And there's another one. Oh, I should have had this link ready and I apologize. Oh my gosh. What is the one I'm looking for here? Oh my gosh, I am so tired today. Sorry, I'm blanking on this right now and I didn't have my notes written down. Oh, there we go. Van Allen belts. All right. And so this is a very interesting thing. So maybe I'll just start showing this one. All right. And so here is the Earth and some magnetic fields surrounding the Earth. Great. All right. Now, what we see here, you see a bunch of different arrows representing the Earth's magnetic field and a bunch of squiggly lines representing particles. So if I could, let's get down to here. All right. I want to just play this animation really quick. So here is the planet Earth. We see some magnetic field lines here. And what's going to happen is you could imagine, say, a charged particle, some kind of ion is going to be coming here, a charged particle. Let's just say it's a plus ion for right now. Well, what do we know about plus charges and magnetic fields? They tend to go in circles and take helical paths around the magnetic field lines. We've seen this before. However, when the field gets stronger, the increasing field strength can act effectively as a mirror and cause this thing to be reflected and bounce backwards. And this can trap cosmic rays and prevent them from crashing into the Earth. And the idea is these ions go in these helical paths. Let me get rid of that. And we could see an ion getting trapped in the Earth's magnetic field, and instead of impacting the Earth, it might travel back and forth like this. So hopefully somebody was able to figure this out and present this, and we've already seen this, but here's an example of some kind of magnetic bottle. This effect can also happen in fluorescent light tubes, if I'm not mistaken, where you'll see the ions curling around inside the magnetic field of a fluorescent light tube. All right. So let me see if I got everything I wanted to talk about for this section. All right, so, oh my gosh. So we've talked a little bit about diamagnetism, paramagnetism, ferromagnetism. We know this is weakest, this is weak, and then this is the strongest. We know that in these two materials, the magnetism disappears when the external field is removed. We know for this one, the magnetism can remain after the external field is removed. We see diamagnetism is repelled by the external field. Paramagnetic is attracted by the external field. And in both cases, I want to make clear, this is a non-uniform, all right? In all three cases, we're talking about non-uniform, all right? Which just means standard bar magnet. And then we see that the ferromagnetism is a little bit tricky because it could attract or repel other ferromagnets, right? Depending on the pole faces, right? A north would attract a south pole, but it would repel a north pole. And we saw that it can also attract non-magnetized materials, right? So the paper clips that were not magnetized were suddenly attracted because then they became ferromagnets. And we talked a little bit about domains. We talked a little bit about the Earth's